Alright, let's go. Number 10. TON 618. In the distant universe, there is an object so massive, so grotesque in scale, that the moment you understand what it actually is, the word large loses all meaning. TON 618 is a quasar, a black hole so enormous it has swallowed 66 billion solar masses, not stars, solar masses, each one the mass of our entire sun. Now try to picture the event horizon, the point of no return, the edge of the abyss. It spans 1/300 astronomical units across. Our entire solar system, from the sun to the outermost reaches of the Oort cloud, fits inside it, comfortably, with room to spare. You could drop our entire planetary neighborhood into TON 618, and it wouldn't even register as a ripple. Here is the problem. According to everything we understand about black hole formation, TON 618 should not exist. Black holes grow by consuming matter. There are hard physical limits on how fast they can eat, a ceiling called the Eddington limit, where the radiation pressure from infalling material pushes back against incoming mass and throttles growth. To reach 66 billion solar masses, TON 618 would need to have been consuming matter at maximum theoretical capacity for nearly the entire age of the universe, without pause, without interruption, perfectly efficiently. The models say that's not how it works. Something fed this thing in a way we cannot account for, and it sits out there in the dark, 10.4 billion light years away, too enormous for our physics to comfortably explain. Number 9. The black hole at the center of galaxy M87, 6.5 billion solar masses. And on April 10, 2019, we took its picture. The Event Horizon Telescope, a planet-sized array of synchronized radio dishes, stared at M87 for years and assembled a single, fuzzy, orange ring of light. The shadow at the center confirmed general relativity with stunning precision. Einstein was right. The geometry of space-time around a black hole matched the equations almost perfectly. Almost. What the image also revealed was the jet. M87 fires a beam of plasma from its poles straight out into intergalactic space, stretching 5,000 light-years in length. That jet travels at 99% the speed of light. Nothing can travel faster than light. That is not a law of physics that has exceptions. And yet, when astronomers measured the apparent velocity of that jet across the sky, the speed it appears to move from our perspective, it clocked in at faster than light. Superluminal motion. We know this is a geometric illusion caused by relativistic effects, the jet moving toward us at such a steep angle that it tricks our measurements. We understand the math, but understanding it doesn't make it less disturbing. The universe found a way to make something look impossible even when it isn't, and that's unsettling in its own right. Number 8. Sagittarius A. The black hole at the center of our own galaxy, 4 million solar masses, 26,000 light-years from Earth. In 2022, the Event Horizon Telescope photographed it too, another fuzzy orange ring, another confirmation of general relativity. And then astronomers got quiet. Here's what should be true. Sagittarius A sits inside a dense region packed with gas, dust, and stellar debris. There is material everywhere. A black hole of 4 million solar masses, surrounded by fuel, should be actively feeding. It should be blazing. It should be a quasar. The center of our galaxy should be lit up like a cosmic furnace, pumping out energy across the electromagnetic spectrum, visible from across the universe. Instead, Sagittarius A is almost completely dormant. It barely whispers. For a black hole its size, in its environment, the output is roughly 1,000,000 times less than it should be. Astronomers have a term for this. They call it starvation. But that's not an explanation. It's a description. Why is it starving? There's food everywhere. Models suggest the accretion process, the spiral of material falling in, might be incredibly inefficient at this scale, most of the gas getting expelled before it crosses the horizon. But every model is a guess. The real answer is, we don't know. The black hole at the center of our own galaxy is almost completely silent, and we cannot tell you why. Number 7. Intermediate mass black holes. Black holes come in two sizes, that's the rule. Small ones form when massive stars die, typically between 5 and 100 solar masses. Large ones, supermassive, inhabit the centers of galaxies, millions to billions of solar masses. The physics of formation is different for each. The gap between them, from a few hundred to a few 100,000 solar masses, should be nearly empty. Our models say it's almost impossible to form a black hole in that range. You can't grow a stellar remnant that fast. You can't shrink a supermassive down. The gap should exist. It doesn't. We keep finding them. Intermediate mass black holes. IMBHs, lurking in globular clusters, hidden in dwarf galaxies, scattered through regions where our models say they have no business existing. Some are 1,000 solar masses. Some are closer to 100,000. Every time we find one, we update our models, and then we find another one that breaks the update. There is no agreed mechanism for how they form. Some theorists suggest runaway stellar mergers, a chain reaction of stars colliding in dense clusters so fast that a single object accumulates intermediate mass before it can explode. Others suggest they're the remnants of population 3 stars, the first generation of massive stars in the early universe. Nobody has confirmed either. The gap we thought was empty is full of objects that shouldn't be there. Number 6. GW1FIM0914, September 14, 2015. Two black holes collided 1.3 billion light-years away. One was 29 solar masses, the other was 36. They had been spiraling toward each other for billions of years, accelerating, radiating energy as gravitational waves, until they finally merged into a single black hole of 62 solar masses. The math is immediately wrong. 29 plus 36 is 65. The merger produced a 62 solar mass black hole. 3 solar masses, 6 million trillion kilograms of mass, vanished in an instant, converted directly into energy, into gravitational waves. In 0.2 seconds, that collision released more energy than every star in the observable universe combined, every star, simultaneously. For a fifth of a second, 2 black holes outshone the entire cosmos. The shock wave hit Earth. It arrived as a distortion in space-time, a compression and stretching of the fabric of reality itself. The LIGO detectors measured it. The displacement was real. 4 kilometers of laser interferometer arm, stretched and squeezed by a distance 1,000th the diameter of a single proton. We detected a ripple in space-time from a collision that happened when multicellular life was just beginning on Earth. Einstein predicted gravitational waves in 1916. It took us 99 years and the most sensitive instrument ever built to confirm it. The universe sends us messages. They are written in the geometry of space itself. Number 5. The black hole information paradox. No object, no measurement, just a crack running straight through the foundation of physics. Quantum mechanics is the theory of the very small. It has been tested to greater precision than any other theory in science. One of its core laws: information cannot be destroyed. The quantum state of a system, every particle, every arrangement, every property, must be conserved. You can scramble it, transform it, disperse it across the universe, but you cannot eliminate it. General relativity is the theory of gravity and space-time. It has been tested to extraordinary precision. One of its core results: anything that crosses a black hole event horizon is gone. The information about that object, its quantum state, its history, its properties, is trapped behind a boundary from which nothing, not even light, can return. And when the black hole eventually evaporates, that information is destroyed. Both theories are correct. They have never failed a test. They give incompatible answers. This is not a minor disagreement. It is a fundamental contradiction at the heart of physics. Stephen Hawking spent 30 years on this problem. In 2004, he conceded he had been wrong to believe information was destroyed, but he couldn't fully explain how it escaped. Leonard Susskind argued it was preserved through a mechanism called black hole complementarity. Juan Maldacena proposed it escapes encoded in Hawking radiation through something called holography. Every solution introduces new assumptions that cannot yet be tested. The problem is not solved. It is managed, and that is a very different thing. Number 4. Hawking radiation. In 1974, Stephen Hawking calculated that black holes aren't permanent. They glow, not with light from infalling matter, from quantum effects at the event horizon itself. Virtual particle pairs constantly flicker into existence at the edge of the void. Normally they annihilate each other instantly, but at the event horizon, one particle falls in, one escapes. The escaping particle carries away a tiny amount of energy. The black hole loses mass. Slowly, impossibly slowly. A stellar mass black hole takes 10 to the power of 67 years to evaporate completely. For reference, the current age of the universe is 10 to the 14. We are not close to observing this. But if Hawking was right, and the math says he was, then the evaporation endpoint triggers the information paradox again, harder. Everything that ever fell into a black hole, every particle, every quantum state, every bit of information about every object, has to go somewhere when the black hole finally vanishes. The radiation emitted during evaporation has to encode all of it somehow. The mechanism for this is completely unknown, not approximately understood, not partially solved, completely unknown. Hawking's calculation tells us the end result. It gives no mechanism. The math says it happens. The universe hasn't told us how. Number 3. J05294351. Discovered in 2024. The fastest growing black hole ever found. It is consuming mass equivalent to one entire sun every single day. Not every year. Every day. The accretion disk blazing around it is so luminous it outshines its entire host galaxy by a factor of 500 trillion. It is the most luminous object ever identified in the observable universe. The light reaching our telescopes left this object 12 billion years ago, when the universe was less than 2 billion years old. For a black hole to grow this fast, the conditions around it in the early universe had to be extraordinary. A density of available gas, a configuration of infalling material, a suppression of outward radiation pressure that runs counter to every simulation of cosmic structure formation ever run. Early universe simulations consistently produce an environment where black holes struggle to grow quickly. Feedback mechanisms, jets, winds, radiation, constantly disrupt the accretion process. J05294351 ignores all of that. It doesn't just violate our expectations, it obliterates them. It is eating a star's worth of mass every 24 hours, and has been doing so for potentially billions of years. Every model says this should be impossible to sustain. The black hole did not get the memo. Number 2. Primordial black holes. Every black hole we know of formed from something. A massive star dies, the core collapses, a black hole is born. That is the mechanism. That is the rule. Primordial black holes have no mechanism. They are theorized to have formed in the first fractions of a second after the Big Bang, not from stellar collapse but from density fluctuations in the primordial plasma itself. Regions where matter was packed just slightly too tightly, collapsing directly into black holes before stars, before galaxies, before any structure existed. They could range from microscopic to millions of solar masses. They have never been confirmed. We have no direct evidence they exist. But here's what they could explain. Dark matter. The invisible substance making up 27% of all the mass in the universe. It doesn't emit light. It doesn't interact electromagnetically. We know it exists only from its gravitational effects on galaxies and cosmic structure. We have never detected a dark matter particle. Every dedicated experiment, Lux, Xenon, Pandax, has come up empty. And some physicists now believe the answer is not a new particle at all. They believe the dark matter is primordial black holes. Ancient, invisible, cold, distributed through every galaxy. The darkness between stars might not be empty. It might be filled with the silent remnants of the universe's first moments, waiting, undetectable, everywhere. Number 1. The black hole at the beginning of time. The James Webb Space Telescope has found them. Supermassive black holes, containing hundreds of millions to billions of solar masses, existing just 400 to 600 million years after the Big Bang. This is not a surprising discovery, it is a catastrophic one. Here is why. The universe itself is 13.8 billion years old. At 400 million years post-Big Bang, the first stars had barely switched on. The first galaxies were primitive, small, just beginning to assemble. For a black hole to reach a billion solar masses in that time frame, it would need to start from a seed black hole and accrete continuously at maximum theoretical efficiency, the Eddington limit, never exceeding it, never dropping below it, perfectly, without interruption, from the first moment of its existence. The numbers don't work, not approximately, not close. They fail completely. There is no known physical process that can grow a billion solar mass black hole in 400 million years from any seed we know how to create. The theorists have tried. They have proposed direct collapse black holes. The idea that in the early universe, conditions occasionally allowed gas clouds to collapse directly into massive black holes without forming stars first, producing seeds of 10,000 to 100,000 solar masses instead of the typical handful. Even that doesn't close the gap. You still can't grow fast enough. You still run out of time. The math refuses. Which leaves two options, and neither is comfortable. Option 1. Our understanding of the early universe is catastrophically wrong. The physics of the first billion years, the processes of structure formation, the behavior of matter and energy in the primordial cosmos, we have it fundamentally backwards. Option 2. These black holes did not form in the early universe. They existed before the processes that should have created them, before stars, possibly before galaxies, possibly from conditions that predate every structure we have ever modeled. The black holes found by JWST may be older than the stars themselves, and if black holes can exist before the mechanisms that create them, then we are not dealing with a gap in our knowledge. We are dealing with something forming outside the story of the universe we thought we understood. 10 black holes, 10 places where the equations shudder, 10 discoveries that didn't just push the edges of our knowledge, they found the edges and revealed there's nothing behind them. Black holes are not just objects in space. They are the locations where physics itself breaks down, where time stops, where information vanishes, where the two greatest theories ever constructed by human minds, quantum mechanics and general relativity, look each other in the eye and contradict. Every event horizon is a wall, and on the other side of that wall, our maps end. We have sent our best equations to the edge. They came back blank. Whatever is happening inside a black hole, whatever emerges when they die, whatever created the monsters JWST found at the dawn of time, the universe knows. We don't. And for now, that silence is the most terrifying thing in physics. If you want to see more videos like this, click the video on screen now.